Hi, and welcome to this video where we're going to talk about radian measure. This is just a short little introduction to radians. We're going to look at what a radian is, how it works, why we use it, where it comes from, and we'll look at some quick examples. This is perfect if you've just met radian measure along the way. So, for example, an applied math student who's met radians in circular motion, or maybe you have started trigonometry in Leaving Cert Higher Level Maths and want to know more about radians. So what is a radian? So imagine a circle with a radius of r, and if you measure an arc along the edge of the circle that's exactly the same length as the radius, that will have created one radian. So here is our visual for it. So one radian is where we have an arc length equal to the radius. So we can generalize that further and say to find the size of an angle in radians, we always divide the arc length by its radius. So that will give us theta in radians. So when we're working with radians, you'll often see it abbreviated to RAD as the unit. And that's to identify that we're working in radians. However, it doesn't actually have a measurement per se, because if you think about what we have here, the arc length is measured in SI units as a meter, radius also meters. So this angle in radians is actually a ratio rather than having a specific unit. Like I say, we do use radian or RAD to stand for it to identify when we have radians. So you've probably spent most of your life working in degrees. So the most important question is really, how are radians and degrees connected? So here's a lovely little visual. It's our unit circle, and we are starting at 0 degrees, and we work to the left. We're working anti-clockwise, and we can see some of our main angles. Now, not everything is there. We're missing our 30 and our 60 and so on, but you can see that we have 0 degrees or 360 degrees, and we're getting 0 or 2 pi radians. Most of the time we can identify we're working with radians because we see that pi. If you're working in your log tables, page 13 is great, and this table in particular is a great connector for degrees and radians. I'd always suggest to any of my students who are working in maths or applied maths to have this page open in front of you if you're doing any work with radians. If you put in enough time and effort, you may start thinking in radians. However, it's more likely, even by the end of your 2 years, you will be thinking in degrees and translating to radians, which is absolutely fine. So keep this page open to help you. So just to give you a little bit of background about radians. So there's an 18th century origin. So the concept of radians emerged in the 18th century as mathematicians sought a more natural way to measure angles. So Roger Coates, he was an English mathematician who introduced this idea, and this idea of radians connecting the radius to the arc length. It is, I suppose, very much a natural way of measuring our angles. I know degrees may feel more natural because you've been doing them. However, keep in mind that 360 is quite an arbitrary number to divide a circle into that many parts. So if we think about radians, and we'll ask bigger questions about the why, but one of the big reasons we have radians and they've been so successful is because they have created a much simpler approach when we're in calculus. So if you haven't studied calculus yet, don't worry, you will. However, if you have seen calculus, you'll know that we always use radians when working with any trigonometric function. It simplifies the whole process, and actually a lot of our rules are based along radians rather than degrees. So radians really is the universal standard for any kind of advanced mathematics, physics, engineering. We do generally see a mix at Leaving Cert, at both higher level Leaving Cert and in applied maths. We see a mix of both degrees and radians. So the actual language around it, so the word radian is coming from um, the word radius, which means ray or spoke of a wheel, which is a really nice kind of visualization. It's very connected into that idea of circles. So I suppose, why do we use radians? Well, radians really do simplify mathematical calculations. Now, you may not believe that. You may find yours easier. But if we actually look objectively, the calculations when we're working radians are much, much easier. They're a much more they're a much more natural way of thinking. They connect back to our circle in a way the degree does not. So angles measured in radians reveal the hidden simplicity of circular motion and calculus. So you won't get through applied maths or higher level maths without having to have some knowledge of radians. So what I would say is just embrace it. It is weird, it is new, it is different, but very much doable for what little we have to work with them. So why not degrees? So 360 is a really, really arbitrary number. We have taken a circle and divided it into 360 parts. Now, we would never do that if that was happening this day and age. We would probably divide it into 100 because we work in quite a decimal kind of world. We like things in batches of tens. The 360 comes from the ancient Babylonians, who would have loved that number because it had so many factors. That was really their draw to 360. But I suppose when we really think about it, 360 is a random number, and just because you're used to it, you're familiar with it, you may not be questioning why 360, but it is a bit bizarre. So degrees are less useful in calculus because there isn't a direct connection, and that's really it. 360 is just so like a random number. It's not connected. When we talk about radians, we're connecting back the size of the angle to the circle itself. So it's just a much more natural approach. So in calculus, we use radians because we're looking at how things change. So it's important that if we're talking about how things change, we're talking about how they change in relation to what they're in. So for example, the angle changing in relation to the circle. So that would be important for us. So we're going to look at some questions now. I'm going to jump straight in using page 13 first, and then we'll work on some calculations using a conversion. So I'm going to show you how this page 13 is so useful. So the first thing we're going to do is we're going to try and convert 150 degrees to radians using, at the bottom of the page, you can see what I've taken from page 13. So there's a few different ways we can do it. The first way I'm going to look at is using multiplication. So 150 can be written as 5 30 degrees, which is 5, and instead of 30 degrees, we can put in pi over 6. When we're multiplying fractions, you multiply across the top, across the bottom. Remember that 5 is like 5 over 1, so we get 5 pi over 6. Lovely and straightforward. So for 300 degrees, we're doing something similar. We're going to do 10 by 30. Or we could do 5 by 60. So let's do 10 by pi over 6. So this gives us 10 pi over 6. However, this can be simplified because I can divide a 2 into the top and a 2 in the bottom. So we get 5 pi over 3. 15 degrees is 30 degrees divided by 2. So if we are putting that in radians, that's pi over 6 divided by 2. So when we want to divide by a fraction, instead we can multiply by its reciprocal. So that gives us pi over 12. You're absolutely fine to divide it straight in if you're happy to do that. But when we're working with fractions, it's a nice little trick. To divide by a number, we can instead multiply by its reciprocal. Reciprocal means we flip its fraction. Remember, 2 is 2 over 1. So then we have 195. So I'm going to do some addition here. So this is like having a 45-degree angle plus a 60-degree angle plus a 90-degree angle, which in radians is pi over 4 plus pi over 3 plus pi over 2. Now, if you're feeling a little bit lazy and don't particularly want to go along and get a lowest common denominator, which would be 12, you can put this into your calculator with the pi's, Or without the pies, you can literally add a quarter plus a third plus a half and then stick your pi back in. I'm actually going to convert them all to 12ths. So 3 pi over 12 plus 4 pi over 12 plus 6 pi over 12. When we add fractions, we just add the top. The denominator is just telling us they're 12ths, and we get 13 pi over 12, which makes sense because that's just over 1, and 1 pi is 80 degrees. So let's see if we can go the other way using page 13. So pi over 3, lovely and straightforward, that's just 60 degrees. Now we have 2 pi over 3, so that's like having 2 pi over 3's, which is 60 degrees, which is going to be 120 degrees. So then we have 7 pi over 4. Let's pull that 7 out. So that's 7 pi over 4's, which is 745 degrees. And when we multiply that out, we get 315 degrees. And 3 pi's are going to be 380 degrees. So that is going to be bigger than a circle. Now, here's the thing. You may not be aware that you can have more than 360 degrees. What effectively 540 means is we start here, we rotate, so that's 360 degrees, and then we go an extra 180, so we end up here. So the angle is kind of equivalent, or looks like it's 180 degrees when we look at it on a circle. However, if you've looked at functions, you will know how this continues on. If you haven't seen functions yet, I would say to you, you will. So what if we don't have lovely, nice numbers that we can work with page 13? Well, page 13 can still help us because the main connection on page 13 is 180 degrees equals pi. So we have two ways to convert. We either convert from degrees to radians, and to do that, we're going to multiply by pi over 180. And if we want to convert back, we divide by that fraction, or an easier way to think about that is multiply by its reciprocal. So for degrees, you divide by 180 degrees, multiply by pi. For radians to degrees, we divide by pi radians and multiply by 180 degrees. So here, if I have 151 degrees, I'm going to multiply by pi over 180, and that will get me my answer. So let's do 151 pi, and we're going to divide that by 180. That is literally 151 over 180 pi. But if you want to change that to decimal, which is absolutely fine to do, we would have 2.64 radians. So now let's do 310. So let's do 310 divided by 180 multiplied by pi. That gives us 31 pi over 18. And converting that to a decimal, 5.41 radians. So 7 degrees multiplied by pi over 180. That gives us 7 pi over 180. So 7 pi over 180, and we're going to get 0.122 radians. And our last one is multiplying 400 degrees by pi over 180. When we do that, we end up with 20 pi over 9. If we convert that, we get 6.98 radians. So then let's convert from radians to degrees. So this time we're multiplying by 180 degrees over pi. So this gives us 180 divided by pi. We would never leave pi in our answer here. Pi is only really reserved for our radians. So this gives us 57.3 degrees. So what about 1.5 radians? So we do 1.5 by 180 and divide that by 2 pi, and that's giving us 42.97 degrees. 0.1 of a radian, so let's multiply that by 180 over pi. That's giving us 5.73 degrees. And our last one is 6 radians. So we're going to do 6 by 180 and divide that by pi. We get 343.77 degrees. So the last thing we're going to look at in this video is how we have some formulas for the area of the sector and length of an arc, which work with radians. We can see that this first formula here is a rearrangement from the formula we first saw at the start of this video. We're going to focus on that formula for the next two little examples so we can see how we work with radians and the length of the arc. So I left the formula up here at the top. Calculate the arc length for a circle with the radius 10 meters and an angle of pi over 2 radians. So we're looking for L. Our radius is 10 and this is pi over 2. This gives us 5 pi. However, we wouldn't leave our answer in terms of pi for a length. So instead, we're going to change that to a decimal. So it's 15.7 meters. So part B then is a sector of a circle has an arc length 15 meters. So this time they've given us L and they've given us the angle and they want us to find the radius. So our L is 15, our R we don't know, and then we're multiplying that by pi over 4. So R is going to be 15 times 4 over pi. And then if we work that out and change that to decimal, we get 19.1 meters for our radius. Thanks for watching. I hope you found that video helpful. Don't forget to check out the other videos on the channel. If there is anything that you are looking for that you can't find, feel free to leave me a comment below. If it's on my channel, I will send you the link. If it's not there, I will do my best to get the video put up.